So today we're going to talk about trig integrals. Depending on the book you're using, this is chapter 8.3 from the Briggs book, or if you're using the Stewart book, this would be chapter 7.2, I believe. So just kind of look at trig integrals in your book, whatever section it is. So I'd like to write out, so I wrote out the first like 8, antiderivatives or integrals for the trig functions that I feel like you should know. The first 6 are obvious, like you should for sure know those. But I think 7 and 8 are less common. I don't use them very often. It's kind of a, it's something you definitely have to force yourself to learn. So I would say 7 and 8 might be new to some of you. Some of you may have seen it before, but you don't use it a lot. Again, I'm not going to use like 50 of these, but it is something that you guys want to know. It should be something you memorize for calculus. Now, I know some of you, since you have your notes, you may think you don't have to memorize it, but eventually you will want to know these. It's kind of like, not knowing your times tables. If you don't know your times tables, then you're always trying to figure stuff out that other people are already passed. If you don't know your integration tables, or the core basic, like 20 to 25 of them, you're always going to be kind of behind when other people already know, oh, this integral is this derivative. It's really important to understand the relationship between the derivative and the antiderivative and how to hop back and forth, okay? But I did want to give you guys 2 new formulas that you may not have seen. So again, write these down. These should be in your notes. This is something you should know. And the 2 new formulas that I'm going to give you are the integral of secant x dx and the integral of cosecant x dx. Okay, so if you notice, those aren't up here. There's secant x tan x and cosecant x cotan x, but not just, oh, and there's also secant squared and cosecant squared, but there's not just plain cosecant and plain secant x, okay? So secant, the integral of secant x dx is worth the natural log of the absolute value of secant x plus tan x plus c, and the integral of cosecant x dx is equal to the natural log of cosecant x minus cotan x plus c. So very similar in their nature. One uses the secant, one uses the cosecant, one uses the tan, one uses the cotan, one uses plus, one uses minus. This is kind of some patterns you guys probably start noticing, that secant goes with tangent and cosecant goes with cotangent. You should have started noticing that last semester in Calculus 1. So I just want to show you guys where one of them came from. The other one would be derived in a very similar fashion. So let's suppose that we have the integral of secant x dx. So what I'm going to do is something that we learned in a previous section. I'm going to multiply by a special 1, and I'm going to multiply by secant x plus tan x divided by secant x plus tan x, okay? And what I'm going to do, and if you're sitting there thinking, well, how are you supposed to know to do that? Honestly, when I first took this class many, many years ago, I didn't know that that would work on this problem. So these are things you develop over time. You see other people, what they came up with. Obviously, there had to be somebody that was the first to think of it, or maybe there was just hundreds of thousands of people all trying to figure out these new formulas. But for us, we're going to try to kind of take some knowledge that was already gained and get a deeper understanding of it. And then from there, maybe you guys, as you go further in mathematics, could develop your own ideas and formulas and things like that once you have kind of the core basics. So this is one of the core basics. Multiplying by 1, right? This is something all of you know how to do. It's just sometimes you don't think that it works as well as it does in certain situations. But I hope you're seeing that multiplying by 1, or sometimes even adding 0, does a lot for a problem, okay? So let's distribute this. So this is going to become secant squared x plus secant x tan x all over secant x plus tan x dx. So all I did was I distributed it, okay? And the thing is what I'm going to do is I'm going to declare u to equal a secant x plus tan x, okay? Now you might say, why? Why would you do that? Remember, the whole point of u substitution is you always have to think ahead of the game. You always have to think, whatever you declare u to be, what would the derivative of that become? So if I let this be secant x, then the derivative, what's the derivative of secant? The derivative of secant is secant x tan x. And what's the derivative of tangent? Well, the derivative of tangent is secant squared x. Now look at this dx. Look at this, and then look at this. It's literally the same thing. So by doing this, by thinking ahead of the game, by thinking, well, if I let u be this, what would du be? The only way you could do this is if you kind of knew all the derivatives and the antiderivatives off the top of your head. You have to know that the derivative of tangent is secant squared. You have to know that the derivative of secant is secant tan, right? Secant x tan x. So now what I'm going to do is I'm going to rewrite this as the integral of du over u, right? I mean, think about it. This piece right here, all of this is just du, oops, and that. And then this piece right here is just u. So it's du over u. It seems simple, but that's what u sub does. It makes a very complicated problem look simplistic. So now this becomes the natural log of the absolute value of u plus c. But we said that u was secant x plus tan x plus c. And that's where the formula came from. So basically in about one u sub, we have the problem, okay? It's just sneaky. And then the idea of multiplying by a special one. So this is the key for this problem, okay? All right, so I just wanted to show you where one of these formulas came from. So now you have to add these two new formulas to your mental. You have to make sure that you have those in there. You may not have to know them instantly, but when you see secant and cosecant integrals, you should not be scared of them anymore because you now have a way to deal with them, okay? So let's take a look at something a little bit further along in trig integrals. So what if you were given this problem? This is kind of turning the page now. We're working with a different problem. We're not with secants and cosecants. So we have cosine cubed x dx. Let me just put this so there's no confusion. Okay. So pause the video and think of how would you guys try to integrate this? There's probably going to be some kind of u sub, but it's got to be a u sub that's set up just right. Okay, so pause the video and let me see what you guys got. All right, so hopefully you unpause the video and you rewrote this problem as sine squared x cosine squared, oops, cubed, squared was correct the first time, cosine squared x times cosine x dx. Okay, now the thing is with this style of problem, remember when you're dealing with u, whatever you declare u to be when you're working with sines and cosines, du will be the other one. So if one's sine, then du will be the other one. But the problem is I can't have a du squared, right? So I can't say, well, if u is equal to sine of x, then du is cosine cubed. You know, it's not going to work like that. So what we need to do is we either need to make everything sines or we need to make everything cosines. Now, you see how right here I rewrote cosine cubed as cosine squared times cosine? What I'm going to do is an old technique where I'm going to save one for later. Okay, so you might have done this in Calc 1 with trig problems, but a good technique is when you have an odd power for your cosine or sine, sometimes you should make it take one of those odd powers, move it off to the side. So now you have cosine squareds and sine squareds. The reason for that is you guys know this formula, sine squared x plus cosine squared x equals 1, oops, not 0, equals 1. So you could solve for sine squared x and you get 1 minus cosine squared x, or you could solve for cosine squared x and get 1 minus sine squared x, whichever you need for whichever problem. But in both cases, you need it to be an even power, a squared, a fourth, a sixth, whatever the case may be. When it gets above squared, you know, there's just a little more work to it, but that's the general idea behind it. So what I'm going to do is I'm going to rewrite cosine squared as 1 minus sine squared. So this becomes sine squared x times 1 minus sine squared x cosine x dx, right? Now think of this real quick. Whatever you're about to let u become, du has to account for all the rest of it, okay? So if I let u equal cosine of x, then du has to be all of this, and that's not going to work, okay? So if I let u equal sine of x, then what's du? Du would be, oops, du would be cosine of x dx. Look at that, okay? So then this can become this, and then this goes right here and right here. So let's see what we got in this next step. So this would be the integral of u squared times 1 minus u squared du. And all I did was this became my du, this became that, and this became that. You guys see? So now I have just a little u sub problem that I can distribute real quick. This becomes u squared minus u to the 4th du. Okay, so you know what, let's go over here a little bit. So now we have u cubed over 3 minus u to the 5th over 5. And it's no limits of integration, so it's plus c. But we know that u was worth sine, so this becomes sine cubed of x over 3 minus sine to the 5th of x over 5 plus c. Okay, and that's it. That's all you do. So what you notice was the key was to focus on the odd power. So what we did was we focused on whichever one had an odd power, okay? Whichever one had the odd power, we took one of those powers and moved it off to the side. And then we tried to rewrite everything in terms of we tried to rewrite everything in terms of one set of sines and cosines. I said it backwards. You want to rewrite everything either as sines or either as cosines. Okay, so that's kind of the goal of this when you're dealing with sine and cosine. And again, I don't have some foolproof plan that always works, but this is a good strategy to start. Okay. So let's look at another problem. Oh, this one's a little bit harder. So this one is sine cubed of 4x. Okay. Now dx. Now here's the thing. It's an odd power. So once again, I'm going to rewrite it as sine squared x. Oops, 4x, I'm sorry. 4x sine 4x dx. Right? So it's still basically using a similar idea from last time, but it looks nicer, but I think this one's actually harder. Okay, and then what did we do last time? So whatever the du was going to become, the other thing had to become the u, right? So in this case, the sine 4x dx is going to become the du, right? So right here. So that means that sine squared 4x has to be in terms of cosine. So when we take the derivative of it, we get back to sine, which is the ending. So what I'm going to do is I'm going to say u equals, oops, not u. I'm going to say that this is the integral of 1 minus cosine squared 4x times sine 4x dx. So again, all I'm doing is I'm using this trig substitution right here. These trig subs right here are very powerful. The Pythagorean identity works really good. So we have 1 minus cosine squared 4x. So we know that last time what worked was u is equal to cosine 4x, du is equal to negative sine 4x dx times 4, right? Because of the chain rule. So then I'm going to have to divide real quick by 4. Okay, so now we have d over 4 is worth a negative sign. You know what? I'm going to divide by the negative 4 too. Okay, I'll divide by the negative. So now when we do our rewrite, we're going to have the integral of 1 minus, now the cosine of 4x is going to be u squared. And then we know that this is negative 1/4, so times negative 1/4 du, right? Because sine x 4x dx, sine x 4x dx is worth negative 1/4 du. All right, so now let's see. Yeah, that looks good. So now this will become negative 1/4 integral 1 minus u squared du. Let me just double check, make sure I'm not missing anything. I think that's good, yeah. So now let's keep going. So this will be negative 1/4. The integral of 1 is u minus u cubed over 3 plus c. Okay, so let's keep going. What did we say u was? We said that u was cosine 4x. So this will be cosine 4x minus cosine cubed 4x over 3 plus c. Yep, and that's it. And you could distribute if you wanted. You could do this as cosine 4x over 4 negative plus cosine cubed 4x over 12 plus c. That's both of these are correct answers. It just depends on how it's asked to be entered in. Okay, so this gives us a little bit of guidelines that we can use. So let me write out these guidelines for you guys. And this is guidelines. These are not mathematical all the time, 100% work. These are things that we use in mathematics that help us, that lead us to in the right direction. A lot of people want like absolutes in math, like it's absolutely always going to be this no matter what, but it doesn't happen often. There's very few things in math that don't have little flaws in them. Some like a little thing that says, but this has to be true. Even with integration, it has to be continuous function. Otherwise, we have to call it an improper integral, and then we got to work with something else. So there's all these little nuances you have to be careful of. So what we're going to do is we're going to say for this form, sine to the m of x, and the m will just be the power, cosine of n to the x dx. Let's use the following. So this is what we'll start with. So we'll start with 1. This will be our first possibility. If the power of cosine x is odd, okay, save a cosine x, right, and express the remaining cosine x's as sine x's. And we use the Pythagorean identity for this, right? Then let u equal sine x, right? So you replace all the cosines with some version of sine, right? Like 1 minus sine squared x or 1 minus sine to the 4th, whatever the case may be. You do that, and then if u is sine x, then du is this leftover. Du is the leftover cosine that you saved for the end. Okay, so that's kind of the idea behind it. Okay, now let's do the second one. Same thing. If the power of sine x is odd, save a sine x and express the remaining. So this is just coming from the other angle, from the other way. Instead of sine, you use cosine or vice versa. Replace the remaining sine x's as cosine x's. Okay, using the Pythagorean identity from before, and then let, you know, this should be a comma probably. Then let u equal sine x. So then let u equal cosine x this time. Okay. So now we have cosine x. So we're going to let u be cosine x. All right. And then the previous one we did sine x. All right. So now step 3 is a scenario we didn't talk about. It said, what if the powers of sine x and cosine x are even? Oops. Here's what we'll do for this one. If they're even, let's say use the following. So you guys memorize these. You may already know them. These are variations of the half angle. I sometimes call them power reduction, but I think the book uses power reduction differently than I do. So let's just call them the variation of the half angle formula. Okay, that's that one. And then, oops. And then we also have cosine squared x is equal to 1/2 times 1 plus cosine 2x. So I believe I may have used this in another problem in the previous part of the class. Some people like to write it like this. I sometimes do this. It's just depending on my mood that day. These are all the same thing, right? So this is the same as this, and this is the same as this, Okay, so in either one of these, what you're doing is you're taking a squared and you're turning it into a first power. Notice these are now first powers, right? So because they're first powers, you can integrate them easier, all right? So that's kind of your go-to move if both of them are even. So let's take a look at one with even. We haven't done one of those yet, I don't think. So let's say we have the integral from 0 to pi over 2 of sine squared 2x dx, okay? So in this case, cosine, there isn't a cosine, so technically you could say it's a 0 power, so that's even. And then sine squared is a 2 power, so that's even. So they're both even, so I'm just going to use my little variation of the half angle. So this is going to become 0 to pi over 2 of 1/2 1 minus cosine 2x dx. Now here's the mistake. I made a mistake right here on purpose to remind you guys. Remember the formula says whatever used to be in here or whatever used to be in here, you double it, okay? You double it. So what used to be in there was a 2x. So what would that be doubled? That would be 4x. So that's the common mistake people make, is they forget to make that 4x. Okay. So then, let me see here. What I could do is I could say this is 1/2 integral of 1 minus cosine 4x dx. I actually did this differently another time that I did it, but this should be okay. Yeah, I think this is okay. Okay, so now what I need to do is I need to split it. So this would become 1/2 times the integral of dx minus 1/2 times the integral of cosine 4x, limits of integration from 0 to pi over 2, pi over 2, 0 to pi over 2. So everything's good now. So then what we're going to do is we're going to do a little u sub on this. So u is equal to 4x, du is equal to 4 dx, divided by 4, divided by 4. So now we have our new, oops. So right here, we're going to end up with 1/2 x from 0 to pi over 2. This will be minus 1/8 times the integral of cosine of u du. So then we're going to keep going, 1/2 x. I won't integrate this yet, pi over 2. I mean, I won't plug in f of b minus f of a yet. So this will be minus 1/8. Oops. Let's see here, 1/8 sine of u. But what did we say u was? U was 4x from 0 to pi over 2. So I can do this as one big one now. Let me see here. So this would be 1/2 times pi over 2. So this would be pi over 4 minus 0. F of b minus f of a minus 1/8. And then this would become f of b would be sine of 2 pi, which is 0, and sine of 0, which is 0. So this would just end up becoming pi over 4. So our final answer would be pi over 4. All right, so that's how you can do it when it's an even power. And again, it looked kind of innocent, but look at all the work I had to do. You might be able to skip one step here, maybe two, but you guys got to show me something. Yeah, you got to show me something, so you should be okay. All right, so let me look at another one. Yeah, that should be that. Let me give you, what do we do if we have tangent? So let's say we have the integral of tan, ooh, this one looks bad. Let me see, let's do tan squared x secant to the 4th x dx. So we'll have a little bit of rules for these guys as well. I have a worse one that we can talk about in our next meeting, but tan squared x secant to the 4th x, all right? So for this one, we have to think ahead of the game. Whatever u is, the derivative of it. So if I let u be secant, then I would get secant tan, you know, kind of all over the place. But what if I let u be tangent? Then the derivative of tangent is secant squared, and we have secant to the 4th. So I feel like I have a way to deal with that. So what I'm going to do is I'm going to say, well, this is actually tan squared x secant squared x times secant squared x dx. So I'm going to save a secant squared now because I know the derivative of tangent. I know the derivative of tangent is secant squared. So if I let u be that, but then I still have this extra secant here, I can't have two du's, like a du and another du. So what I'm going to do is I'm going to do a rewrite, just like we did before. And I'm going to rewrite this as 1 plus tan squared x times secant squared x dx. And there's other ways you can do it, you guys. You can try to do u sub right off the bat and then substitute in. It's just preference. I prefer to do all this and then u when I'm done. To remind you, all I'm doing is sine squared x plus cosine squared x equals 1. If you divide this problem by cosine squared, oops, this becomes tan squared plus 1 equals, now 1 over cosine is secant squared x, right? So then tan squared x plus 1 is equal to secant squared x. So I just did that replacement right here, right? That's how I fixed it. So if you're wondering, you just use that little property. It's a variation of the Pythagorean identity. You just got to do the work. If you're dealing with cosecants, then you do the same thing, but divide by sine instead of cosine. Okay. So let's do some rewrites here, or not rewrites, but let's clean this up. You know what, I'll leave it like that. And let's say that u is equal to, remember the whole point was we wanted u to be tangent. Because if u is tangent, then we know the derivative of that is secant squared x, and we know that is that guy right there. So it works perfectly into our u sub. Hopefully, again, you guys, I'm hoping you understand why I emphasized u sub so much the first week of school. U sub just comes up in everything, okay? Because a lot of things deal with composite functions, and U sub is your way to deal with composite functions. Okay, so we have this. Now the thing is that when I go to substitute this in, I'm going to get U squared times 1 plus U squared, I'm sorry about that, and then du. So then this is actually the integral of U squared plus U to the 4th du. And then this is actually u cubed over 3 plus u to the 5 over 5 plus c. But then you guys know that u was tan x. So this becomes tan cubed x over 3 plus tan to the 5th x over 5 plus c. Yep, sounds good. And that would be our final answer. So we were able to work with secant and tan using a similar idea and approach, but this time we saved a secant, okay? So let me give you guys a little bit of set of rules for this. So it says, if we have integrals of the form tangent m of x, tangent to the m of x, secant of the n, or I'm sorry, to the n of x dx. So we have rule 1, or guideline 1, if the power of secant x is even, save a secant squared x and express, now this should sound familiar, right? This is exactly what we did, express the remaining secant x as 10 x's, okay, using that identity that I just gave you, and let u equal 10x. So that's what we just did, right? Okay. Now, if you do this next one, this other scenario is if the power of 10x is odd, save a secant x tan x. So you write a whole chunk, a secant x tan x, off to the side and express, express the remaining tan x's as secant x using the same identity, tan squared x plus 1 equals secant squared x, and let u equal secant x. Okay, so this should get you started on most of these style of problems. Again, it's not perfect, it's not foolproof, but it's a good way to start. Let's look at one that looks a little bit different, and let's see how hard this one actually is. Okay, now this one, I think I'm going back to sine and cosine. I don't use the secant and cosecant or in tangent as much, but I just saw this one in my notes and I thought this would be a good one to do for you guys. Let's see, yeah, I like this one. So here's one more with cosine. So let's say we have cosine to the 5th of alpha all over the square root of sine alpha d alpha. Okay, now we're going to use similar thinking once again. So in this case, cosine is odd, so we go up here. What does it say when cosine is odd? If the power of cosine is odd, save a cosine. So we're just going to follow our rules. And again, you don't need these rules, guys. This is just an idea. If you already kind of thought of this on your own without me telling you, more power to you to do it. So this will be cosine to the 4th of alpha times cosine to the 1st of alpha all over sine alpha d alpha. So all I did was I rewrote a cosine of alpha. You know what, maybe I should write it a little bit nicer. Let's do this. Square root of sine alpha times, let's write that cosine alpha so it's just obvious, right? That this is going to be what our du is, right? That's the idea behind it. Remember, we're saving one so that we can name u the sine, and then the du will be the leftovers, or vice versa. However, in this case, it said that if you're going to let u be sine, then that means everything else should be rewritten similarly. So we have to find a way to rewrite cosine to the 4th. So we know that cosine to the 4th is actually cosine. Let me do the scratch work over here for you guys. So we have sine squared, let me do it in a different color. Sine squared x plus cosine squared x equals 1. So we could do cosine squared x equals 1 minus sine squared x, but then we could square both sides, right? We could square this and square this, and then we would get cosine to the 4th x, but that's equal to 1 minus sine squared x squared. So I'm going to do that. I'm going to rewrite my cosine to the 4th as 1 minus sine squared x squared all over the square root of sine, oops, this isn't x, I'm sorry, it's alpha. Sine of alpha d alpha. Oops, cosine, I keep forgetting. Cosine alpha d alpha. Now remember, we're purposely saving this guy for the du, so we just got to keep holding on to it. Now we're going to let u equal sine alpha. So then du is equal to cosine alpha d alpha. And again, we have our perfect, this is perfect, right? So that means, let's rewrite this. We have the integral of 1 minus u squared all over, now sine of alpha square rooted is u to the 1/2. And then du is the leftovers. Well, I got to do a little bit of work here. This becomes 1 minus 2u squared plus u to the 4th all over u to the 1/2 du. But that is, if I divide that, that's actually u to the negative 1/2 minus 2u to the 3/2 plus, what would that be? 8/2 minus 1/2, so it'd be 7/2, u to the 7/2, right, du. Now the thing is we actually haven't integrated, but some students mess up right here because they feel like they just integrated, but we haven't. We haven't done any integration, we've just cleaned things up. So now we have to integrate. So this will become u to the 1/2 over 1/2 minus 2u to the 5/2 over 5/2 plus u to the 9/2 over 9/2 plus c. So let's see what this cleans up to. So this will be 2. Now we said u way over here was sine alpha. So this is going to be 2 sine alpha to the 1/2 power minus 4/5 sine alpha to the 5/2 power. Yeah, I think it's 5/2 power, yep. And then plus 2/9 sine alpha to the 9/2 power plus c. So I think I made a little mistake in my notes. That's why I paused. I think my notes, I just had a mental typo. For some reason, I put 4/5, but it's to the 5/2. Let me clean this up. Okay, you guys, so that's one of the weirder ones. And again, see what it looked like originally. Originally, it looked like cosine to the 5th alpha over square root of sine alpha, which doesn't kind of look like what we're dealing with here, but there was still a way that we could manipulate it. Okay, so just keep an eye on all of that and make sure you kind of understand. These problems aren't easy, but once you kind of get the pattern, and it's all about these trig subs. Now, what if you don't know all your trig identities that I'm using? You got to learn them. There's quite a few trig identities you're supposed to know already. I'm not even talking calculus. I'm just talking things that you were supposed to learn in trig. So let me know if you're having trouble, and we can talk about it. That's going to do it for this video, guys. I'm going to post this one for you as well.